Hey everyone, welcome to my channel. Today we got plenty of time that we're gonna use to revise on legal question, and I'm gonna crack some hard question, and it's gonna be fun. Let's watch it. So right now I'm doing this question, which will be the larger rectangle in histogram, and I felt like maybe it would be best for me to explain my solution while I do this question because it's more like interview scenario. And here's what I'm gonna do. So for this question, it's I think so we have to like analyze this question first. The question, what this question meaning is that I give you whole lot of array that each index represents the height of the block in the index, and then we want to return the larger rectangle in this histogram. And this graph is very intuitive and it explains the situation. And also about this graph, same. And then you found this graph, like you will immediately understand that yes, there might be like more than one solution, but they're only interesting in the area of larger rectangle. And the next thing we want to do is we look at those parameter, and here the length is 10 power 5 and the height is 10 power 4. And I don't think height is matter much here, and the length is what we care, which will be the length of the array, and it's 10 power 5, and we can maximum to ON login or ON solution. And I think it's important. And for this question, I mean, like the immediate idea come to my mind is that we want to sort of like generate a one-take solution, which is I expect this index, and then we can determine that the maximum rectangle can be formed by this index, and then we move to next index to do it in ON step. But right now, we cannot do it because we don't know like the maximum rectangle can form in particular index. So we might want to do some pre-processing, and then I was thinking like to do so, like we can observe that suppose that we want to expand our rectangle on the right, then we have to have the block of code, I mean the block of like a grid or this bar to be greater or equal to this rectangle. And then we want to continue to find the first rectangle bar that's smaller than this the index we're expecting, and we should stop there. So I'm thinking like before we do this, like before we do above the action we did, we want to first find the maximum like the length is expand on the right and expand on the left, and then when we got those, then we can calculate the maximum rectangle can be formed by one particular index in one time. And above step can show, I mean like it should be done also in ON, then ON times complexity, and then we will derive ON algorithm. Or it can be ON login, but I really don't see why we need to ON login because yeah, just not really like if you want to sort it to determine it, then it's kind of like break our like it's not really fit in this question scenario because hey, the position does matter in this problem. And in particular problem, I recall that we want to use a DQ or a deck or like a queue for this sort of problem to like maintain some data structure, but I couldn't really understand like how do I able to justify the correctness of our algorithm. So right now I'm thinking about this. So I'm saying that for the queue, I want to maintaining. Oh, so like what I'm doing right now is like I want to do it in two separate operations because I found like it might be hard to do it in one go, one take. So yeah, I might just do it in two takes. And in this maximum expand left array, we want to store that each index, how many the maximum index I can expand on my left side. And similar, just like vice versa for this one. I want to store the maximum index can we expand on the right hand side. Yeah, that's like the idea for this problem. The next problem is like how do we do that? And I'm thinking like using a queue, that's my answer, but like right now I want to justify it. So I want to say like for the queue I can maintaining a decrease in format, then suppose then we claim first like If it's in decreasing format, then I want to claim that first element that wait a second. I feel like it's not decreasing format because something went wrong. I feel like increasing format. But increasing format is a bit counterintuitive. So suppose we can simulate a bit. So suppose that is like 2, 1, 5, 6, 2, 3, and in our simulation, first element would be 2 and second element 1. Then we would pop out the first element and make it 1. Then store 5, 6, and then it's 2. Then 2 will pop out 6 and 5 and 2. Oh, I think I like, yeah, that makes more sense. So it's not decreasing format, it should be increasing format. And now I can re-justify it. Suppose that we got an array like that, but we just like use 3 dot dot to represent more elements, and then suppose that we got also maintaining an increasing format. And the operation we do is that suppose we inspect an element that has a greater than for our format would be like 1, 2, 3, like dot dot 2 like x, and then suppose that we are expecting an element called y at this this index. So this our q is not represent the index, so I should put it aside to make it like to not confuse the mark it as our q. And then suppose we are inspecting this element just called y, and then suppose there's few scenario here. Suppose y is greater or equal to x, then what we do is then we put x into our queue. And then the second situation is like suppose y is more than x, then we pop our element to find the position for y such that y is greatest element. Yeah, looks reasonable for me, and then we can justify why we do that. So suppose that we also go this queue, just like 1, 2, 3 to x, and then we want to find the first element smaller than y, because that's our objective. And then if suppose we can find this element, then we can calculate like the range we can expand. And here first element way smaller than y. Oops, I just wait. First element smaller than y. I'm thinking like I can do it in O1, but seems not. Seems I cannot. Seems here I need to use a binary search here. Yeah. But anyway, hey, we'll continue to this problem, and yeah, up to here, we want to prove the correctness of this algorithm, and then I'm thinking like using binary search to find the last element smaller than y. Then we can re-justify why this index is like why this index is correct. Suppose we can do it by contradiction. Suppose there is an index that smaller than y and have a greater index or smaller index. But we can do it in 2 steps. So suppose that there is an index that's smaller than y and have a greater index. Then suppose it's smaller than y, then because you have a greater index, right? Then we have to done this operation onto the index before. I suppose I got a greater index, and then here we can clearly see that if y equals smaller than x, then we should replace this element with y. So yeah, this wouldn't happen. And then we have second contradiction. Suppose that zero is index. Actually, this one can be is like a trivial case. Like if it have a smaller index, then very unlikely we cannot use that index because they couldn't expand till here. I'm not sure if I understand this, but let me give an example. So suppose that we go like 1, 2, 1, 2, 3. So in this case, we can tell like, oh yes, we can expand to here. I mean, we cannot expand to here. Then we should stop here. Yeah, and whatever the expand should be like whatever on the right of this index. That's what we did. And then the first case, like a contradiction, the first contradiction is like, oh, we can find a smaller or equal element that is, wait a second, oh, here, yeah. We want to be strictly increasing instead of non-decreasing. This is like trivial case, but it's important. And here, suppose that we can find an element that is greater than this element and have a greater index, but also like smaller than equal to this. Then suppose that another 2 here, then in this operation, this number will replace this number's position, so it wouldn't happen. We can always find that in our binary search. Yeah, if the same element, we take the element with greater index, and then suppose that there is another element that's smaller than this index, then it doesn't matter because our expansion already stopped here. It cannot go further on F. We just do not consider any index that have smaller value. Yes, I think that's it. So that would be our theory, and then we can like implementing it. Let's have a queue, and then we call it minimum left. Oh, yeah, I already created it. So yeah, and name is exactly the same. Yeah, let's do it. And for yeah, I just realized something. So we can observe here. So we want the value, yes, but we're also interested on its index because only by getting its index, I can tell like how much left I can expand. So instead of using a queue, here I want to use a pair of int. And the first can be represented the height, and second can be represented by its index. Yeah, great. Yeah, let's do it. So what we can do is for int I equal to 0 as more, just like traversing this heights, and yeah, let's do the left one first, and the right should be very similar. And base case, if I equal to 0, then what we do is q the push back, I think. Or maybe it's push. I don't know. I might be running stupid. Heights I push this pair into our queue. Yeah, something went wrong. Maybe it's push back. Oh, damn it. Stupid. I'm not using the correct variable name. Yeah, let's fix the issue. Just push, and then besides push, what else we can do? We do nothing because if it's first element, then basically it couldn't expand, right? Maximum expand left. Also, yeah, there's another problem into this thing. It's like if you are using a queue, then if it's using a queue, can we do binary search on queue? Maybe we should use vector. Yeah, let's use vector. Then push back. That's the only difference. Oh, great. And yes, and then else. Case 1. Y greater than x. So if a number that's greater than x, then we just push it back. And also here, we find the current maximum element. Obviously, it cannot expand on left. Yeah. Height I is greater than minimum left side minus 1. If it's greater than some, we just push it back. Trivial case. Oh well, what happened here? Invalid operand, so oh yeah, the first. Well, using a pair here. So yeah, and then we just push it back. Else, otherwise we have to. Oh, I was thinking you spend a search, but I realized something. So while we're updating the queue, we are actually like sort of doing it. Like after we update the queue, the first element will be smaller than the current element, and that's when we should stop. And also we got the index. But I'm thinking like something about it. Yeah. No, I'm thinking like a trivia case, but I think I'm already too much. But anyway, forget about it. And then we just do. Later I will do a new time complexity analysis for this scenario. I feel like, how to say it's like, although it's on, but each time we do this operation, we actually like decreasing the size of our array. So overall, there will be maximum on kicking action like this kind of kick action we would take. So the time complexity actually is better than the binary search one. Yeah. Minimum lift. So I should do like smaller equal to height I. If minimum left door side greater than 0, and this thing happens, and we just kick it out. How do we do kick it out? Let me search it. C++ vector delete last element. Put back. Okay, it's very intuitive. Put back then. Yeah, put back. And then we now get maximum expand on left. So here we need to consider trivial case, which is when there's no element inside of our queue. Then maybe we can declare here maximum expand. Let's initialize to be 0, and then maximum expand will equal to I. Yeah, it will be equal to I because all element before it is smaller than it, so you can expand all the way to the front, so it would be I. It should be I minus 1, I think. Yeah, I think it should be I minus 1. It makes more sense mathematically. I'll take it as I minus 1. Else, maximum expand equal to I minus the first element in our queue. I mean, like in our queue, right? Will be minimum left this thing, the first. And this time you need +1, right? You need +1. Do you need +1? You don't need +1, yeah. That's what I'm thinking. You don't need +1 because you want to calculate the maximum expand on the left. So you can expand 1 to make it become less 2. So this is our trivia case. It does not matter that much. And lastly, of course, we need to insert our new index into our queue. And after this for loop, we should get maximum expand left working. But I'm a bit shaky about my results, so let's print it out and see if it works before we actually submit anything. -1. Oops, so this one. Okay. Oh, something went wrong. All right, I have this maximum expand, but I didn't put it. So that might be right. Wait, -1, -2. Oopsie, second. Yeah, that's right, dumb mistake. So wrong, but it's more fully correct, I would say. Maximum expand left, so this 2 should able to expand by 2. Otherwise, it will be correct. We can sort of simulate the situation, so our array should be 1, 5, 6. And then when we insert in 2, then it should kick out this 2 element and find this 1. So yeah, then it should be 2. But right now I'm getting a 1. Yeah, that's really interesting. And yeah, let me think about how do I fix this problem. Yes, I ran stupid. Equal to 0. So I feel like this is wrong. I couldn't prove it. So this I represent the index, and then it can expand on its left. So yeah, let's try if we saw -1. -1 doesn't make too much sense here. Although it doesn't change the result. Height is greater than the last element of first, then we just push it back. Otherwise, if I equal to 0, therefore push back. Yeah, this is like our trivia, like first case. So nothing went wrong here. Nothing could went wrong here. So if height we inserting a greater element, then we just push it back. Also, nothing went wrong here because if it's like if you don't kick out an element, that means that you are the current maximum, then you cannot form anything on the left hand side. Yeah, and then you sort of kicking element. And when inserting 2, I feel like I should Mobility. This might be some trivial case. Smaller equal to this. Wait a second. What's next about it? Might be running stupid here. So I'm gonna print it out to see what I have done wrong. Index and last index. So 1043. So when expecting 1, it should be 0 and give me 1. Makes sense. When expecting 4, give me 3. That makes sense here. So here I should be handle this. So minimum left is it's maybe it's greater or equal. Yeah, I think I know why I moved the order and that's run silly mistake. Oh well, and let's get rid of this and print it out to see if my result is correct on the expand left hand side. Okay, should have a -1 like I did before. This should not have -1, but here showed. Great, and it's working, and the logic for expand on right should be very similar. In fact, I'm gonna copy paste it. Oh. I think the logic is all the same, so I might just like change left to right. Oops, I get -3. Yeah, I kinda know what went wrong. And wait a second. Did I make sure I change everything? Oh well. Yeah, I wonder what went wrong. How could probably be -5? Doesn't make sense. Okay, let's see here. Two, 5. At the index 2, I stored to be 5. That's weird. How? Ah, freak. That's very stupid. I didn't change all my variables name. I believe it should work because the logic is basically identical. What? No way. Dude. Did I modify everything? Okay, let's see here. What? Oh, right, makes sense. So I'm still maintaining increasing order. Oh, right, that's why I'm confused. That's why I'm confused. So it's correct here. Actually correct. Yep. So then it should be -I -1. Maximum expand. How the heck did I get -5? That makes sense. Yeah, that makes sense, but -5. What? How the heck did I get -5? What? Wait, let me print out this result. Right, if this is so freakish, unbelievable, then I might just well print the result. I'm pretty sure result is the problem. At least. So I should understand how the string stream working. Oh well, 2, 5, 4, 1. 1 is correct. X. Oh wait, 1 is correct. Freak, 1 is correct. This will went. I'm like, yo, this is what went wrong. When went right. Ah, freak. I show you. Oh my. I try stupid. Show is height or size -1. That's why. And now should be correct. So yeah. I mean, come on, it's a hard problem. So yeah, don't be surprised that you see me debug wrong time. But hey, it seems to be correct. And then that we can do it int max rectangle. Initially we set it to be -1, then for we want index equal to 0 and minus height the sides. Then blah plus. Great. Max rectangle equal to max, and the max triangle we can find the maximum expand left I plus maximum expand right I plus 1, and this whole thing times by the height. Return max rectangle. Boom. Great. Seems working. And let's try some edge case. So can height be 0? Oh, it can. Maybe insert a few 0 inside of it and see if it's still correct. Seems correct, and then we can just like copy paste to, like the test for more cases. Great, and then maybe you can try something different. We use the same height. Yeah, let's do same height and see if my thing is still working. Oops, add up comma. Surprisingly, it's still working. I mean, I shouldn't be saying surprisingly. It make like my answer is not very confident. But hey, it's working. To make it more safe, I'm gonna use a wrong. And here, let's do this. It seems working. I'm gonna submit. And it is working. Time complexity is fine. It's not that good. I'm seeing. To be honest, it's like so. I'm pretty sure like in time complexity sense, I'm using the best the best algorithm. But in my implementation, I'm not doing the best. But hey, I think that's it for this problem. Thank you for watching. I'm gonna stop recording and post this question as individual question, but I'm gonna do the next question.